Picture this. You're sitting in the exam hall, the clock is relentlessly ticking down, and boom, there it is. A massive, high-mark computer science past paper question on binary addition and overflow. Now, panic sets in for most students right about here, but not for you. Today, in this explainer, we are channeling our inner John Wick. We're becoming the boogeyman of grades. Because when those really tough, scenario-based questions try to push you out of your comfort zone, you're going to push back with precision-engineered answers. We're going to completely dissect the anatomy of the perfect response so you can transform vague theory into absolute grade-scoring mastery.
Okay, here's our roadmap for securing those top marks today. First up, we'll cover the trap. Then, the strategy reveal. Third is the transformation. After that, we'll dive into an interactive workshop. And finally, we'll lock it all in with the final system. Let's jump right in.
Section 1, the trap, the illusion of knowledge.
I want to challenge you right out of the gate. Think about this specific question. What exact digital problem does binary overflow solve? I want you to stop just reciting facts for a second and really think about the practical consequences here. Because in the real world, overflow isn't just some harmless math error on a piece of paper, right? It's literally a catastrophic failure waiting to happen. What data is involved? What specific device is failing? What's the practical consequence for the user? When you start answering those questions, you turn basic terminology from something you just blindly memorize into a powerful, meaningful tool. Let's look at two classic student profiles falling into this exact trap. First, we have Alex. Alex loves data dumping and writes, "An overflow error happens when the binary number is too big for the computer." Then we've got Sam. Sam is rushing, completely misses the command words, and just writes, "Overflow is an error." Well, both of these answers totally lack precise terminology. They fail to explain the process, and they completely ignore the real-world context. They're just generic. And let me tell you, generic does not survive the examiner's red pen. Section 2, the strategy reveal, decoding and structuring. And before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, this brings us to the golden rule, coming directly from the examiner's checkpoint itself. Generic responses rarely gain full marks. Listen, context is everything here. If the exam prompt is asking you about an embedded system inside a massive industrial robotics factory, your answer absolutely must stay inside that specific context. You've got to explain how the overflow error might cause the robot's arm to miscalculate its position and, crash into a wall. Anchoring your explanation to the specific details provided in the scenario, that's the secret sauce that unlocks the higher grade boundaries.
To do this consistently, we use a super disciplined 4-step path. Step 1. Identify the requirement. Ask yourself, is this asking for a process explanation or is it logical reasoning? Step 2, classify the relevant element. Are we dealing with hardware or software here? Step 3, explain the process in a clear, logical sequence without skipping any steps. And finally, Step 4, connect the explanation back to the context. This sequence seamlessly moves you from basic recognition to deep understanding and finally to high-level application.
Now, to execute those 4 steps perfectly in your writing, you need the ultimate structured weapon. We call it the PEEL framework. That's point, evidence, explanation, link. First, you make your point by stating the core fact. Next, you provide evidence by pulling specific data straight from the exam scenario. Then, give your explanation of exactly how the technical process works under the hood. And finally, link it all together by explaining the ultimate consequence. If you follow PEEL, every single sentence you write is strategically designed to extract a mark. So let's test this out. Which of these two hypothetical approaches sounds like it actually uses PEEL? Is it approach A, which just vaguely says the system crashed because numbers got too big, or is it approach B, which points out the drone's altitude sensor, explains the exact 9th bit generation, and links it directly to a calculation failure? Yeah, it's obviously approach B. That is exactly how you need to structure your writing to strike with absolute precision. Section 3, the transformation, securing the green check marks. Let's break down a classic fatal mistake I see all the time. The before answer simply says, memory gets full. This fundamental misunderstanding costs so many marks because it confuses general memory with a specific register. Now listen to this after rewrite. The 8-bit register exceeds 255, in binary, all ones, causing an overflow error during arithmetic processing. Just listen to the precision in that. We specified the 8-bit register, we gave the exact maximum values, and correctly identified the arithmetic process. Guys, this is a bulletproof response.
The real secret to writing like that under intense exam pressure is using context anchors. Real-world transfer matters so much. Just imagine a banking system where an overflow error turns a massive positive balance into a negative one just because a single sign bit flipped. Or think about a secure communication protocol that drops vital packets because the sequence number exceeded the register's capacity. When you link this abstract concept of overflow to a concrete, real-world disaster, the theory instantly becomes memorable and totally ready to deploy on exam day. Okay, now it's your turn. Remember Alex from earlier, who wrote that generic, an overflow error happens when the binary number is too big? How would you rewrite that flawed paragraph right now using our PEL framework? Think about it. You'd want to identify a specific register, right? Explain the ninth bit generation, and then link it to a system crash. If you just constructed something mentally that explicitly mentions an 8-bit limit failing and generating an extra bit, you are well on your way to securing top marks. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4, Interactive Workshop. Let's test your mettle. Challenge 1, Data Scan. Let's run a mental simulation here. What is actually happening when things go wrong? Let's say we add a binary 1 followed by 7 zeros to another 1 followed by 7 zeros. What do you actually get? You get a 1 followed by 8 zeros. That is 9 bits. But remember, your CPU register is strictly 8-bit. So that 9th bit, the most significant bit, is pushed right off the edge into the absolute void. It just vanishes. And that data loss, that is the exact technical definition of an overflow error. Challenge 2. Find the flaw. Listen to this sentence carefully. Binary addition combines bits, but sometimes the result doesn't fit in the storage, causing the program to stop. Okay, where is the fatal flaw there? It's the word storage. Students bleed marks by describing secondary devices like an SSD or a hard drive here. Binary arithmetic happens in the CPU's registers, which is the form of immediate memory. So switch the word storage to CPU register and you instantly save your grade. Challenge 3, Speed Writing. Let's mentally draft one perfect PEL paragraph right now about an overflow scenario in an embedded temperature sensor. Ready? Point. Overflow occurred. Evidence. The 8-bit temperature sensor exceeded 255 degrees. Explanation. The addition generated a 9th bit that could not be held in the register, resulting in a loss of the most significant bit. Link. This caused the sensor to misread a critically high temperature as a low temperature, failing to trigger the cooling fan. Boom. That is exactly how you dominate an exam scenario. Section 5, the final system, your exam success blueprint. We've done the heavy lifting today, but honestly, none of this matters if you just forget it all by next week. Our foundation here is the highly effective 3-pass revision cycle. Pass 1, secure the key definitions and contrasts. Pass 2, rehearse worked explanations. Seriously, don't just read them, map out those 8-bit binary additions by hand. Pass 3, test adaptability. If you practiced with a drone scenario, try answering the same exact concept applied to a digital thermometer. This proves you have true mastery, not just fragile short-term memorization. To really enforce this cycle, I want you to use the 4-prompt memory structure. Before you ever consider a topic finished, you need to answer these 4 questions aloud. What is it? It's an arithmetic error where the result exceeds register capacity. How does it work? A 9th bit is generated in an 8-bit system and gets lost. Where is it used? In CPU calculations and embedded sensors. Why does it matter? Because it causes critical logic failures. If you can run through this diagnostic checklist smoothly, your understanding is basically unbreakable. Let's summarize the 3 unbreakable rules of our answering system. Rule 1, command word decoding. Diagnose exactly what the task is demanding and stay completely inside the context provided. Rule 2, PEL framework application. Every single high-mark answer must have point, evidence, explanation, and link. No more generic data dumping. Rule 3, time management matrix. Allocate your structured responses according to the weight of the grade. Please don't write a novel for a simple 2-mark question. Let me be very clear about the impact of this system. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. It is the absolute difference between just knowing the theory in your bedroom and actually being able to execute a flawless technical explanation under the intense pressure of the exam hall. Mastering these concepts requires dedication, review, and active engagement. If you can decode the command words and apply the Peel framework, you turn even the most intimidating questions into an opportunity to shine. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at actheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. So I leave you with one final thought. Are you going to be the victim of the exam or the boogeyman of grades?